All right, so good afternoon, everyone. As Professor Irene said, we are Neptune, and we designed a nanocomposite for demulsification of oily wastewater, specifically designed for the crude oil industry. Essentially, what we'll be going over today is an introduction to the problem in oily wastewater in this industry, the disadvantages of current filtration techniques, nanocomposite design, verification and validation of our design, as well as our conclusions. So, what is oily wastewater in the crude oil industry? Essentially, it takes the form of water and oil emulsions, with oil being the continuous phase. So essentially in light crude oil, the water content within it is about 5 to 20% volume of emulsions within it, and in heavier crude oil, ranges from 10 to 35%. So the way they're formed is they're formed in many different stages of crude oil production, in extraction, refinement, upgrading, and transportation of this crude oil, and produced by the turbulence and agitation of the oil and water mixture. So essentially, if we wanted to just get rid of the emulsion, we can easily dump it, but at the same time, it is actually costly because we want to keep as much oil as possible to refine it into petroleum products. So the way we do it it happens by, there are many different techniques. The first one, commonly being chemical demulsification. I must provide the four main actions of creating a strong attraction to the oil and water interface, flocculation, coalescence, and solids wetting, with the most common with demulsifiers being esters, diapoxides, urethanes, and resins. So the technique that we are actually trying to improve upon is the filtration technique for demulsification of crude oil and water emulsions. So what essentially a filter is a material with a pore space ratio, and preferentially, it should allow in our case, should allow the oil to pass through and block the water from actually passing through the filter itself. Current technologies that are used in membranes are polymeric membranes and ceramic membranes. Polymeric membranes are actually quite inexpensive, but they actually foul quite easily, and they are very thermally and chemically unstable and therefore degrade. As well as ceramic membranes, have better separation, they actually foul a lot, and they're actually quite expensive to clean or replace and maintain. So the requirements that are required from industry are listed up here above. Our filter must at least have a separation efficiency of about 90% weight, superhydrophobicity, superoleophilicity, compressive strength of about 2 megapascals or greater, and it must be able to separate microemulsions, which range from 300 nanometers to 20 microns, because this is actually one of the most common emulsions found in the oily wastewater and crude oil industry. It will also be favorable if our filter was able to withstand the processing temperatures found, which is about 40 degrees in the crude oil industry, as well as the solution has about a pH of 8.5. So the solution, our design for the nanocomposite is combining PVDF and HBNNS, so hexagonal boron nitride nanosheets. These two materials are quite inexpensive. PVDF is a common polymeric membrane material. It is widely studied, and it actually, in certain forms of PVDF membranes, they can actually be hydrophobic and oleophilic. And for hexagonal boron nitride nanosheets, it has high thermal stability, excellent mechanical properties, and it's also quite chemically inert. So when combining these two together, the PVDF with the HBNS combined actually has a dramatic increase in surface roughness, which therefore increases the superhydrophobicity and superoleophilicity of the nanocomposite, as well as provides improved chemical, thermal stability, as well as mechanical strength. Also, the way that the synthesis route that we use should be really easy to scale up in order to use it for large-scale industrial applications.
Composite, with the application in mind, we expect the four following trade-offs. So the first one being production cost versus the performance, the porosity of the material versus its mechanical strength, the separation efficiency versus the pore size distribution, and also the energy input in terms of applying a pressure gradient or heating up the emulsion versus the time it takes for the emulsion to pass through. So our synthesis composes of two parts. The first part is the exfoliation of bulk HBN. So we just disperse it in water, sonicate it, and then purify it through centrifugation and collect it with freeze drying. The second part is the actual fabrication of the nanocomposite. And so we disperse the HBNNS in NMP at PVDF, and through a phase inversion process followed by freeze drying, we obtain our nanocomposite. So one of the first things that we try to do to verify our material is we looked at our nanosheets. What were the dimensions? And so we did this using AFM and SEM. And so on the left, you can see the AFM profiles. There is a bit of aggregation, but if you look at profile 4, it gives a sheet length of about 300 nanometers and also a thickness of about 40. And we also did the same with SEM, and we confirmed these dimensions. Next, we also wanted to look at the pore structure and also the morphology of our material through SEM. And so you can see that we have a lot of irregularly shaped pores due to the fact that there are a lot of microspheres that are stacking on top of one another. And so it's a bit difficult to determine what the actual pore size is just because they're so irregular, but it's very obvious that we have a hierarchical distribution of these pores. Next, we did BET to take a look at, or to analyze the pore structure a bit more. And so on the left, you can see the BET isotherm. There is hysteresis, which is characteristic of a porous material, which we do expect. And on the right, you can see the pore size distribution. So apart from the micro-sized pores, we also see that we have a lot of pores around 4.5 nanometers. And this suggests that it could possibly be used for separating nanoemulsions as well. Next, we obviously wanted to confirm that our material was superhydrophobic and superoleophilic. So we did a number of contact angle tests. And with the water contact angle, we found that it was greater than 176, which is quite impressive. And to further illustrate this, if this video would load.
Oh, there we go.
Okay, yeah, so it's a little bit laggy, but that's water dyed with methylene blue just rolling off of the surface. And we also repeated this with oil. And unfortunately, because our material absorbed oil so quickly, we weren't actually able to get a good contact angle for it, but it's very obvious that it is superoleophilic. Next, we also wanted to test the chemical stability of our material, and we did this through 3 methods. So the first one being a pH stability test. And we subjected our material to a wide range of pHs ranging from 1 to 13. And we found that after 7 weeks, the material still was very superhydrophobic. And next, for our second and third chemical stability tests, we wanted to make sure that the material would be stable in chlorinated solvents. So we used both chloroform and DCE, which is also known as dichloroethane. And so for chloroform, it just absorbed the solvent and then sunk to the bottom, which is expected because it is an oil-like liquid. And after a span of 7 weeks, we didn't notice any dissolution or degradation. With DCE, we were also interested in seeing if we could clean our material with it. And so on the top there, you can see the filter has wetted a lot with oil. And so it's slightly translucent. And after we expose it to DCE, you can see that it's white again. It's no longer translucent. And so the DCE had displaced the high viscosity oil. And so not only is it stable in chlorinated solvents, but it can also be dried and cleaned and reused. And the last stability test that we did was a physical test. We wanted to make sure that our material would actually be stable in a higher temperature. So we subjected our material to 45°C water and left it there for over 5 hours. And we found, again, that there was no degradation at all, meaning it was still stable.
Okay, so to actually go ahead and test this material, we need to know what kind of good flow rate we can use without generating excessive pressure at the surface that might break it. As I mentioned, a compressive strength is a critical customer requirement, and we need it to be about 2 MPa, which is state-of-the-art PVDF compressive strength. So that would be like our competitor. So our kind of max pore size is about 20 microns, and I'm just reminding you about this because there's an important design trade-off between permeability and mechanical strength, or compressive strength rather. And that is, of course, if you have less material there or you're more porous, you're going to have lower strength. So it's about kind of finding a good optimization point. So there's kind of 3 parameters that are all interrelated to each other, being the porosity, the permeability, and the compressive strength. So what we're interested in doing is modeling the dependence of these 4 parameters on each other. So in terms of the material, that's the porosity, void surface area to total surface area, permeability, same ratio but for volume, and with pressure at the filter surface and the actual flow rate we'll be using. So this is a picture of our setup here. The filter is housed in the white sort of housing there. And you can see that we clearly have two flow regimes in one vessel. So that's Navier-Stokes on the column and Darcy-Brinkman flow through porous media through the filter itself. So before we could actually go ahead and tell the syringe pump to give us a flow rate, we had to simulate what flow rate we want to use. So we went to console. This is actually just what the housing of the filter looks like. You can see the filter is inside. So we went to console, and just to verify that we had the correct sort of flows going on here, you can see we have Stokes on the kind of column, and then Brinkman at the bottom. And that's basically, you expect to see a parabolic velocity profile for standard Stokes flow and a constant velocity profile for Brinkman flow. And what these lines are their different porosities. So when it's more porous, of course, the velocity magnitude through it is going to be faster because there's less material there. So this is just more of a means of validating the model is working. So the actual results. So for permeability versus porosity, that's going to follow the Kármán-Kozeny relation for porous materials, which is shown in the equation in the graph on the right, where the little epsilon is the porosity, capital K is the permeability, little k is equal to 5. That's a Kozeny constant for stationary systems. S is the surface area, which is proportional to 6 over the diameter, all squared. And we just assume spherical pores for the purpose of this simulation. That is obviously a simplification since we have a regular pore size. But what we have actually done is selected like the largest diameter so that we're making that S parameter as small as possible and resulting in bigger permeabilities than we might actually have. So we're protecting ourselves essentially that way, because the pressure we get here, we might actually be able to withstand more than that because we've selected the biggest pores as the average. So the pressure profile at the sort of filter surface is exactly linear with initial flow rate, which is what we expect based on Stokes flow, which is related to the Hagen-Poiseuille equation, where mu is the viscosity of oil, L is the length of the syringe, Q is the flow rate, and the radius of the syringe is R. So from this graph, we were able to get that about 1.2 microliters generates slightly less than 2 MPa. So we went ahead and looked at the pressure at the filter surface, and that's exactly what we find. It's about 1.8 right here. So we actually went to the lab and did this experiment just to see if we did actually have 2 MPa. And as you can see, when we apply a little bit more than 2 MPa, actually, we still have 150-degree contact angle. So our porous structure is maintained, and we're still super hydrophobic. So to actually demulsify, we passed emulsion through a gravimetric apparatus, which is essentially just letting it drip with a small applied vacuum just to push it through. And what you can see here is the emulsion in the sort of micrograph on the right is the emulsion itself. After one pass, we have way fewer oil droplets in there. And then after 2 passes, you can see that, so this was octanol, by the way, as the model oil. You can see that it's actually very clear. So after 2 passes, it looks exactly like octanol, so that was promising. So for the actual test prototype for separation efficiency, we need to quantify this properly. So we used a syringe pump, and that 0.1 ml per min, or 1.2 microliter per second flow rate that we simulated. And we did this with a water and octanol emulsion. The filtration efficiency that we ended up getting was about 80%. So while that is less than the 90% we were hoping for, in industry they tend to stack these things in series. So if you stack many 80% efficient ones, you'll eventually have over 99% anyways. But this is something that we would do for future work, but the syringe pump is very busy in Dr. Pope's lab, so unfortunately we didn't have time to do that. But anyway, as you can see here, all of the high priority and medium priority requirements have been met, with the exception of that 90% I just discussed. And the low priority requirements, being nano emulsions and emulsifier concentrations, were not attempted due to time constraints. So challenges and shortcomings with this, again, separation efficiency of 80%. We should also be testing like many different conditions at the same time, so chemical, thermal, perhaps some applied pressure as well, all at once, see what that does. Also looking at factors that influence pore size and distribution, particularly because the viscosity of like crude oil is a lot higher than some other, in some applications, so the pore size would need to be tuned based on the viscosity. Extending to nano-emulsions and, again, heavy oils and also surfactants. So in terms of scale-up, the synthesis of HBN would be done by ball milling. That's a very standard technique. Then we would be switching to a water ethanol or water methanol for the solvent exchange part in an external coagulant bath. And this is also well established. We calculated the cost of our material, and that's about 26 cents per square centimeter. So that is pretty inexpensive. And in terms of operation, compared to commercial PVDF membranes, ours is actually much stronger. Those have about 1.4 MPa, ours is about 2.4. We would have to scale up the flow rate, of course, consider multiple passes, and the effect of different filter thickness and area. So these emulsions are found in multiple industries, as you can see here, and this may be extended for oil polluter water cleanup as well. So in terms of next steps, just optimizing the pore structure for different viscosities and higher throughput volumes, as well as to get higher separation efficiency, perhaps exploring the effect of different HBN filler concentrations, and see if we can even get out any other contaminants like solids, organics, etc. And of course, engineer filter properties more for nano-emulsions as well. So thank you, and any questions?
Okay, so now the session is open for the questions. Probably we have time for 1 or 2 questions from the audience.
So what is your advance, your technical compared with the current available? What is the path you make a contribution?
So in
Is
terms
it the material? Is it the engineering process? Is it the final, which part is used?
it's both the material and the process. So currently filtration isn't used in the crude oil industry to break up the emulsions, just because it's a little impractical because of the material, because polymeric membranes can't be used with the operating conditions that they use, and the ceramic membranes are too costly, and the cleanup is just impractical, right? So
You invented the material.
yeah.
All material comes together and then
The composite, yeah. So the composite can be used as a filter because the properties, like the strength and the stability, match exactly what's required for the crude oil industry, as well as for other industries, the ways it can be used.
with current membrane. Is it good?
Yeah.
Not good enough. Your impression is not good enough.
So basically, it's not stable for a very long time, meaning that when they try to clean it and stuff, they can't, and they just have to be constantly replacing it. So that's the issue with polymer membranes. And imagine on a big scale, you don't want to be constantly having to replace these things or constantly or have it difficult to clean, right? So as we showed with ours, we can just easily clean it with BCE, just pass that through, it's clean, ready to go.
Yeah, the downtime associated with them having to clean is quite significant in terms of cost, whereas here we are able to actually use the chlorinated solvents typically used in crude oil industry for cleaning and without degradation to our product.
And your calculation is a standard, or is it, for example, you're using emulsion? Is it involves surfactant? Emulsion is what kind of emulsion?
So right now we produce a water and octanol emulsion because we didn't want to complicate this, because for the proof of concept we didn't want to complicate it by using crude oil at the moment. So we used a simple model oil, no surfactants, and we found octanol and water at a 1:9 ratio.
The reason why we used octanol in the first place was if I was to take octane and make a microemulsion out of it, I don't have enough energy in the lab to actually produce the microemulsion the size required. To make it would essentially take a 1 to 9 volume of water to oil, or water to octanol, and then put it under the tip sonicator for about 15 to 30 minutes, about at 100% sonic, at 100% power.
So you don't have surfactant?
No, there's no surfactant. It's purely just a microemulsion that is stable based on the energy. It's
Because you compare with the
Yeah.
other sample.
it's not completely standard because we didn't add surfactants because we wanted to keep our prototype as simple as possible, but we just wanted to mimic the emulsion size that we can actually.
So have you compared with the other? How do you compare
Well, the other ones aren't even used for emulsions. They just use mixtures. So one of the extensions with this project is to do an emulsion.
I mean, what I mean is that any possibility to compare your technique membrane with other membranes.
Right. So
With the standard two sample, you still improve it. Otherwise, it's difficult to claim
Yeah.
you get it developed.
I think probably I should interrupt you because of time handling. Okay, sorry about that. One quick question.
Very nice job, Chris. I have a question about how you envision operating this membrane. So what I got from you have a syringe, and it is your membrane. You're going to push the emulsion through, and it should stop the water, and then allow the oil to go through.
yeah.
Did you do any test with the efficiency with respect to this pressure that you're pushing?
Yes.
What is the pressure required to push water through?
Actually, I think it's about 5 MPa because eventually you will overcome the hydrophobic character of the material, and that's what we saw in with the in-storm testing as well. Once we completely deform the material and it loses its hydrophobic character, so about 5 MPa would be required. With the syringe filter setup, we actually just used the 2 MPa or the flow rate that would be required to generate a 2 MPa pressure at the filter emulsion interface. And so we were able to pass that out. We don't have the calculation. I think it's
When you set up, the water went through or no?
No.
So you just get optimal on the other side?
Yeah. The only shortcoming was with our setup, some of the emulsion and oxygenol was still trapped within the filter just because it's so porous. We just didn't run it long enough. But if we did, we could probably get that remainder out.
Did you try any aromatic thing like a phenol?
No,
We didn't get a
the,
chance to.
yeah,
Okay.
but we did try it.
Okay, so let's move on because we are already behind.
Thank you.
Okay, so let's move on to the next participant. Okay, thank you very much.